Okay, so we're going to talk about energy in physical and chemical changes. Some of this is review when we talk about specific heat, and we're going to learn a few new things about molar heat of fusion, etc. Okay, so just a few thermochemical definitions. Energy is the capacity to do work or produce heat. Heat is a specific form of energy, so thermal energy. That is transferred from warmer to cooler objects. Now you might remember from 8th grade you learned about exothermic and endothermic reactions. So an exothermic reaction releases heat. A good way to remember this is that heat exits. Okay? Now, if I have a beaker and I'm conducting a reaction in that beaker and it's an exothermic reaction, if I held the beaker in my hand, it would feel warm because the reaction is giving off heat to the environment, which includes my hand. An endothermic reaction absorbs heat. A good way to remember this is that heat enters. So if I'm holding a beaker where an endothermic reaction is occurring, it's going to feel cold because it's absorbing heat from the surroundings, including my hand. Okay? Units for energy are going to be joules. The unit that you're probably most familiar with, though, is calories, because when we report energy in food, we do it in terms of calories. But one thing that you may not know is that the calories on your food are nutritional calories, so with a capital C. And a nutritional calorie equals 1,000 regular calories, which is equal to 4,184 joules. So one nutritional calorie is over 4,000 joules. So what that tells you is that 1 joule is a pretty small unit. Okay, so we have energy changes involved in both physical and chemical changes. So in physical changes, you'll see temperature change a lot of times when we dissolve something. Okay, so for example, in the Discovery, we dissolved calcium chloride in water and it got warmer. Okay, so that's an exothermic change. Now, you don't have to know that specific example if you missed the Discovery, so don't worry. But you should know that because the beaker felt warm, it was an exothermic reaction, if that information was provided. Now, if we heat water, like if we boil water, that requires energy in order for the temperature change and then the phase change to occur. Now, we almost always have energy changes occurring during chemical changes. For example, you might remember in Lab 6.2, we mixed copper chloride, the blue solution, and aluminum, and it got quite warm, and that was an exothermic reaction. Okay, so basically, anytime you do a chemical reaction, it'll be either exothermic or endothermic. Now, you might remember these from Unit 5 when we talked about catalysts and activation energy. Okay, enthalpy is basically the, represented by delta H, is the change in energy for a reaction from reactants to products. So you can represent that really well using an enthalpy level diagram or a potential energy diagram. And so on these diagrams, we have energy on the y-axis, or sometimes you'll see it as enthalpy. It doesn't really matter. And then on the x-axis, you see something called the reaction coordinate or reaction pathway, or sometimes it'll just say reaction. And that basically just means this is what happens as the reaction progresses. Okay, so we have our reactants with a given amount of energy. Then we have to overcome activation energy, and then we show our products with a different amount of energy. So enthalpy is the difference between the reactants and the products. Okay? Now, this first one on the left, we have to ask ourselves, is this endothermic or exothermic? Okay, so take a minute and think about it. Our reactants have more energy than the products. That means that energy was given off. So that means this is exothermic. In an endothermic reaction, the products will have more energy than the reactants. Okay? We still have to overcome activation energy, though, regardless. Now, one question that often comes up on IB exams, not that you take one in this course, but is that how does a catalyst affect the enthalpy? Well, a catalyst actually doesn't affect the enthalpy. Remember that a catalyst lowers the activation energy, but it doesn't change the relative energies of the reactants and products. So a catalyst would have no impact on the change in enthalpy of a reaction. Now, when we talk about enthalpy, we want to represent it as negative or positive. So for an exothermic reaction, the change in enthalpy is negative because it's giving off energy. And for an endothermic reaction, delta H is positive. Okay, now these are just some examples of endo and exothermic reactions. We did calcium chloride and water in Discovery 7.1, and the beaker felt warm, so this was exothermic. During this discussion, we did a demo. The beaker felt cold, so that means it's endothermic because it's taking energy from the surroundings, including your hand. Now, boiling water and freezing water are a little counterintuitive when we think about whether they're endothermic or exothermic. So, I just said that if you have a beaker with an exothermic reaction, it'll feel warm. So you might be thinking to yourself, oh, well, boiling water is warm, so that must be exothermic. But boiling water is warm because we're exposing it to a heat source, okay? What we have to ask ourselves about phase changes is energy required for this phase change to occur? So I'd ask myself, is energy required in order to boil water? And the answer in this case is definitely yes. So this is actually endothermic because it requires energy. Conversely, freezing water is actually exothermic because I have to remove energy from the water in order for the molecules to slow down enough for it to freeze. Okay? So energy is released. So those phase changes really can be a little bit counterintuitive, so make sure you think about whether energy is required or released. Now, we're going to tie this back into Unit 6 a little bit. Sometimes you'll get a balanced equation like this, and over here it'll give you an enthalpy value. Okay, so looking at this, I have to think about what I know. It says negative 198 kilojoules per mole is the enthalpy. So first, I know it's exothermic because it has a negative value for enthalpy. Now, what that means is that anytime this reaction occurs as written, I produce 198 kilojoules. So that means that if I react 2 moles of sulfur dioxide, I'll produce 198 kilojoules. If I react 1 mole of oxygen, I'll produce 198 kilojoules. And if I produce 2 moles of sulfur trioxide, again, I'll produce 198 kilojoules. Okay, so if I react 4.5 moles of sulfur dioxide, using these relationships, I can calculate the energy released. I know from the balanced equation that for every 2 moles of sulfur dioxide, I produce 198 kilojoules. Now I can write that with a negative sign like that, or I could say that negative sign in words, right? I could say 198 kilojoules are released. When I calculate that, my calculator gives me negative 445.5 kilojoules. For significant digits, I will round to negative 450 kilojoules. Okay? All right. Let's review specific heat capacity and Q equals mc delta T. Okay, so we learned about this back in Unit 1, so it has been a while. Specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 gram of the substance by 1 degree Celsius. Okay, so the units are joules per gram degrees Celsius. So let's look at a sample problem using this equation that we learned in Unit 1, Q equals mc delta T. An unknown metal requires 4,500 joules of heat to raise the temperature of a 10-gram sample from 0 to 100 degrees Celsius. What is the specific heat capacity of the metal? Okay, so we're going to start with our equation. Now, if you sometimes struggle with problems like this, with word problems, I really suggest you make a list of the variables off to the side and try to define them, okay? So Q is energy in joules, so it's 4,500 joules. M is mass, so it's 10 grams. C is specific heat capacity, and that's what we're trying to find. And in order to calculate delta T, we need the initial temperature, which is 0 degrees Celsius. And we need the final temperature, which is 100 degrees Celsius, okay? And we always calculate delta T as final minus initial. All right, so we get 4,500 joules equals 10 grams times C times 100 minus 0 degrees Celsius. So when we solve for C, we get 4.5 joules per gram degrees Celsius. And when you do a problem like this, you can really see where those units come from, because we're taking joules and we're dividing by grams and degrees Celsius. Now let's look at another kind of a problem where we're going to use Q equals mc delta T, and we're going to look at heat transfer from a warmer to a cooler object. Okay, so let's read the problem. I'm adding 5 grams of aluminum, which is at an initial temperature of 100 degrees Celsius, to 100 grams of water, which is at an initial temperature of 25 degrees Celsius. Now, it wants me to find the final temperature of the water. So, a couple important things here. Now, the first thing that we're going to assume in this problem is that aluminum is going to transfer all of its excess heat to the water. Now, that's probably not true. Some will be lost to the environment, but that's an assumption we can make in this problem. We're also going to assume that the aluminum and the water, when they're mixed together, come to the same final temperature. They reach what's called thermal equilibrium. Just a fancy way of saying once heat transfer is complete, they're at the same temperature. Okay, so based on that assumption, we could say that the heat the aluminum loses is equal to the heat that the water gains, right? So if that's true, then this must also be true. So we're going to set mc delta T for aluminum equal to mc delta T for water. So what I'm going to do is I'm going to, on each side, define the variables. So for aluminum, I know that its mass is 5 grams. I know its specific heat is 0.9. I don't know its final temperature, because that's what the problem's asking me to find. And I know that its initial temperature is 100 degrees Celsius. For water, I know that the initial mass is 100 grams. Well, the mass is 100 grams. The specific heat is 4.18. Again, I'm trying to find the final temperature, and the initial temperature is 25 degrees Celsius. So what I would like you to do right now is pause and try to solve this problem for final temperature. This is really just algebra, okay? So take your time and make sure you know how to do a problem like this, and then we'll go through it. Okay, so to go over this, I'm going to start by erasing everything. Okay, and I'm going to go through the problem a little more slowly. All right, so I know I'm doing mc delta T is mc delta T. Now, algebraically speaking, it doesn't really matter which side I put the negative sign on, but I'm going to put it on the side with aluminum since it's losing heat. Okay, so I'm going to substitute in the numbers that I have. And just to keep this clear, I'm not putting in units. You should, but I just want to make sure that this is easy to follow when you're watching it online. Now, initially, again, it looks like I have 2 variables, but remember, the final temperature for both of these is going to be the same. Okay, so I can collect my terms, distribute, and then I'll collect my terms, actually. Okay, so the final temperature is 25.8 degrees Celsius. And initially that might seem really strange. You might be like, what? I mix something that's 100 and something that's 25 degrees Celsius and I somehow come out with 25.8. But there's two reasons that this makes good sense. So the first reason is that I have much less aluminum than I have water, 5 grams versus 100 grams. The second reason this makes sense is that water has a much higher specific heat capacity, so it takes more energy to change its temperature. So considering those two factors, it's actually not all that surprising. Okay, now, we know how to calculate energy changes when temperature is changing, right? We can use Q equals mc delta T. But we also know that energy is involved when we don't actually see a temperature change. So I'm going to remind you of the heating curve of water that we learned about in Unit 1. And you'll remember in this first phase where the temperature is increasing from -20 to 0, that solid is present. We're just heating up the ice. When the curve flattens out, what that means is that the energy is now being used to change the phase. So we have both solid and liquid present here. The temperature starts to increase again once it's all been changed to liquid. So here this is all liquid. And then we see the temperature stop changing when it's at its boiling point, and that's when we convert liquid to gas. And finally, the temperature will rise again once it's all in the gas phase. Okay? Now, going up the heating curve, these are all endothermic processes because energy is required. Going down the heating curve, these are exothermic. So that can be a helpful way to think about the phase changes. Okay, so there's different kinds of energy involved in the heating curve. So kinetic energy is energy of motion. And this is what's changing when the temperature changes. So as the temperature increases, molecules are moving faster. Potential energy is stored energy. And this is what we're dealing with in phase changes. And you might recall we talked about entropy in Unit 1, that's disorder. And that is increasing as we go from solid to liquid to gas. So what we're going to learn how to do now is to calculate the energy associated with these phase changes. Okay, so we're going to use something called molar heat of fusion and vaporization. So the molar heat of fusion is the amount of energy required to melt 1 mole of a substance. Or, thinking about it the other way, it's the amount of energy released when 1 mole of a substance freezes. The molar heat of vaporization, you might figure out, is the amount of energy required to vaporize 1 mole of a substance. Or conversely, you could think of it as the amount of energy released when 1 mole of a substance condenses. Now, we see molar heat of fusion a lot, but sometimes heat of fusion is just represented in joules per gram instead of kilojoules per mole or joules per mole. So that's fine. It doesn't really matter. We can work with both. We just have to keep an eye on our units to make sure that they cancel out correctly in the end. Okay, so let's look at 2 examples. The first says the substance has a molar heat of vaporization of 498.2 joules per mole. How much energy is required to vaporize 3.5 moles of this substance? Okay, so I know that I have 3.5 moles of this substance. I don't know what it is, but I don't need to in this problem. And I want to figure out how much energy is required for that process. I know that 498.2 joules per 1 mole are required. So I get 1,743 joules with significant digits. I would round that to 1,700 joules. Okay, now here's another example with different units. Substance has a heat of fusion of 102.2 joules per gram. How much energy is required to melt 10 grams of the substance? Okay, so I have 10 grams, and I want to get to joules. I know that for every 1 gram, 102.2 joules are required. So I get 1022 joules with significant digits. It'd be 1020 joules. Okay. Now you could also be given grams and given the molar heat of fusion. As long as you know what substance it is, you could use the molar mass to convert to moles, and then use the molar heat of fusion to convert to joules or kilojoules. Okay, so try the homework and bring lots of questions.